this is a signal, which is also the spike, since if we like transform this z by a transformation, linear transformation A, we get something that is not diagonal anymore, and that's a signal we want to recover from this noisy observation xi. Is there any question on the model? So because of this, because this zi is generated from a zero mean normal distribution, so the expectation of xi equals to 0, and the covariance matrix, let's just call it M for later convenience. It's very easy to see that it equals to AA transpose plus sigma square identity matrix P. All right. So so if we compute the signal to noise ratio here, it turns out that it turns out that the noise the noise is down here, and it is P times sigma square, and the signal is just well K. So when P is large, the signal to noise ratio goes to 0, which means that most of the signal are actually overwhelmed by the high dimensional noise. But this is not a big issue in the high dimensional setting, since we have like this A is only n by k, so we can deal with it, since the first couple of largest singular values will be larger than 1, and based on that, we can recover the underlying principal components nicely with high probability. So sorry. Can you say that again? I was doing that.
Zi is the low-dimensional spherical Gaussian that's transformed by A, and high-dimensional noise is that. That's the
yes. Yeah. This is a so-called spiked covariance matrix model that people use when analyze a standard PCA. It's a very highly cited paper that come up with this model, and usually PCA works beyond such model. And this is different from the deterministic type of PCA paradigm when we assume the output of the SVD is the output of PCA. In the statistical setting, the output of the SVD is just an estimator of the output of the actual PCA. And based on this statistical model, people show that with sample complexity OP, the estimate that's obtained by SVD is actually converges to the like underlying model of underlying covariance matrix of that. Yeah, despite the fact that the noise is really large and it overwhelms the signal in the observation. So the method here is in fact the first method that achieves both the sample complexity and also the memory requirement. Previous methods all work on this by assuming a deterministic setting and are minimizing the regret, and they do not assume anything statistically. So they usually only have the memory like efficiency, but not the statistical guarantee or the other way around. So yeah, but I wouldn't say this paper is like a huge hit to the field because I read it through and there are several buggy points in the proof. So yeah, they need to fix it before it's good. Anyway, the ideas are really complement to what we are learning in class, because Alex, I don't think he really covered a lot on the statistical half of the problem. Yeah. So this paper, what they did is that they extend one of the solvers for PCA, the so-called power iterations, to the streaming setting. So do you guys know what a power iteration is? Okay, yeah, some does. It's very simple, so I just write it down anyway. So the power iteration gives you a way to compute the leading principal component and the largest eigenvalue. So so it initializes Q0 by such that this Q0 has unit norm, and it go into a loop. Yeah, let's just assume we want to calculate. Let's use another. What is a letter that you like? X. Yeah. Suppose this X is a symmetric positive Bentham matrix, and so what one do is to iteratively multiply this X to the randomly generated Q tau minus 1, and then normalize this Q Q tau equals to Z tau divided by Z tau norm. So when this loop converges, meaning that it's when the tolerance is smaller than the threshold, then we have one output, Q tau, and this norm of Z tau gives us the largest eigenvalue. So this is a L2 norm. So this is a so-called power iterations, and it converges linearly. It converges at a speed that is lambda 2 to the power of k. For symmetric matrices, it converges at a rate that has the 2k. And if we use something more sophisticated, this is a so-called inverse power iterations with the Rayleigh quotient parameter mu. You can get like cubic convergence. You don't get cubic convergence often, like because Newton method, you only get quadratic convergence, and this is merely linear convergence. But if you only want to have the largest eigenvalue and eigenvector, you can use this, and the matrix is symmetric, then you can use this Rayleigh quotient iterations and get like cubic convergence. But that's not the point that I'm going to talk about today. Bear in mind that this is only one-dimensional, and the k-dimensional generalization of the power method is the so-called orthogonal iterations. So it's very similar. It initializes Q, which is a matrix in P times K, and instead of needing the L2 norm of Q to be 1, now we need this matrix Q0 to be orthogonal. So again, the algorithm is to loop and iteratively update this this Q by this thing, by multiply this with X times Q tau minus 1, and then take the QR factorization of that. And that gives us the also normal matrix Q tau, yeah. And towards the end, we'll Q tau times R tau. towards the end, we'll output this orthonormal matrix as the first k principal components and the diagonal entries of this R as the corresponding eigenvalues. So this is a so-called orthogonal iterations. It has similar convergence guarantee that goes to 0 at the rate of that. So in this paper, what they did is, in a high level, simply to do such power iterations in a streaming setting by multiplying, by adding like one column at a time. And that gives a good approximation of that, and they show that it's statistically sound. So that's the key idea of the paper. So it's very simple. Yeah. Yeah, the second one can be k eigenvectors. Yeah.
You mean that it adds the column to the matrix of Q?
Yeah, what I mean is that in this paper, their algorithm is to do the power iteration, but instead of multiplying the whole thing together, they they multiply this xt transpose times q. Yeah, one by one. Although this is different to if you do the matrix multiplication together, but it gives you a close enough estimate.
What is changing?
What is changing?
Yeah.
We assume that this x1 to xn comes in one by one. So we see only one column at a time. Then we update this z, and within a mini batch of b, then we update this q by doing this normalization. So I'm going to write the algorithm here because we need to refer to it anyway. There we go. So let me erase this and replace this with a streaming version of it. So is everyone okay with the power iteration and also okay? Good. Yeah. So again, we have Q0. We draw it from a normal distribution, and then normalize it so that Q0 has one norm. L2 norm of Q0 is 1. And then for tau equals to 0, n over b. And b is the number of inner loop, the size of the inner loop iterations, plus 1. And initialize this s tau plus 1 equals to 0. And there's another for loop here. Then they add each and every column by doing this, plus b over 1 xt transpose qt. And after this for loop end, they normalize this s into q by simply q tau plus 1 equals to s tau plus 1 divided by the norm of it. Yeah, this is basically the streaming algorithm for the one-dimensional case. And that's what we are going to prove that actually work. For the more sophisticated version of the algorithm, I'm pretty sure that you can write it out yourself. So we initialize this random Q0 such that this Q0 transpose equals to I. then again it's a for loop. It's the same for loop there. So instead of S a vector here, now we have a matrix S that has the same dimension as Q. And for it's also the same. S tau plus 1 equals to S tau plus 1 plus 1 over B, and the xt transpose, then I times this with a matrix Qt. And what should we have here? After we complete the inner loop iterations, instead of having a normalization, we have the QR factorization. So we get the same thing. That's it. That's the algorithm used in this paper. And streaming PCA is very simple to implement. Just like less than 20 lines of code. Yeah. So now I'm gonna show that why it works and how it works. The model in the one-dimensional case, the model on the top, it's just for each xt equals to some u, and this is just a vector because we only consider the one-dimensional case. The t is again a normal random variable, and this is a random variable in d dimension. And yeah, in this case, the signal-to-noise ratio is 1 over p sigma square. So again, it goes to 0. And the claim in the paper is that when we have this x1, xn generated according to this model, and if we have the number of iterations, that is this value we assign it as a capital T. If we have t equals to, like at a scale of log p over epsilon divided by log sigma square plus 4/3 sigma square plus half. So this is larger than 1, and when we fix a sigma, this can be considered a constant. So essentially, we need this t, the number of outer iterations to be at the scale of log p over epsilon, and we need this b to be at the scale of like 1 plus 3 sigma and sigma square, and square root p, and we have a square term here, and log t, and divided by epsilon square. I'll tell you what is epsilon in a short while. So if these two conditions are satisfied, then yeah, if we times this together, it gives us the sample complexity, which is the number of data points that we need. So n equals to bt equals to roughly like p log p with another log t, and this is log p over epsilon, and there are epsilon and sigma somewhere in here too. So I guess it's either sigma square or sigma to the power of 4 because of this and this power here. And if these conditions are satisfied, then
Shouldn't one of them be O? Like T and V are mostly related, so T is omega, V should be O.
what? Yeah.
So what tau d from t is?
I
Totally different.
I need to multiply them together because t is number of outer iterations and b is the number of inner iterations. B is essentially the number of data points we need to estimate this st before we do the normalization. And t is the number of times we do the entire thing. So the total number of data points we, yeah, so it's n equals to b times t instead of the oh no, it's not that. Yeah, these are conditions. Then with probability at least 0.99. At least that's what they claim. It's kind of buggy here, but if you add a couple of log terms here or there, you'll be able to achieve this. Then we know that the output to the first algorithm we have there, which is the qt minus u 2 norm is smaller or equal to epsilon. So this is what we want based on the model, right? We want to estimate this u, and this says that with the streaming algorithm that we wrote down over there, and if the two conditions are satisfied, that means that we need these many samples, then the estimate of qt is close to what we are searching for in the PCA problem. And the theorem for the second streaming orthogonal iterations is in a similar flavor. So instead of saying the two things are similar, they show that the subspace, their guarantee is like this. It's a qt transpose times, what is that? That's A. But essentially it's a subspace of A. So let me just call it N. This is a ground truth that we are looking for. Operator norm is smaller than epsilon. So this is the theorem, the guarantee for this algorithm. But here today I'm only able to cover the proof for that. Yeah, but the ideas in the proof are very similar. So if you know the simpler version, it's very easy to just work yourself on all the details for the more complicated version. Okay. So is everyone clear with what the claim is in the paper? Yeah. So it's like a sample complexity type of guarantee, and then with some failure probability with 1 minus a small failure probability that it is able to recover the true parameter that we are interested in. So that's the claim. And in order to prove that, it follows a similar flavor to the proof of convergence of strongly convex function using gradient descent. It has a similar flavor to that. So what they did is that they first decomposed this Q tau into two things. They decomposed it to 1 minus delta tau u plus square root delta tau, we call it g tau. This g tau can be different for different tau. And this u is just a true parameter. What this did is to simply project this p tau onto the direction of u, and then project it onto the orthogonal complement of u and get g tau. So towards a convergence, if we want this Q tau to be equals to U, then we will have this delta tau to go to 0. If delta tau go to 0, then these two are the same. If delta tau is small, then the bulk of this Q tau is very close to U. And we have that guarantee, Q tau minus U, 2 norm is smaller than epsilon. So bear that in mind. And oh, by the way, this U and G tau are both normalized so that they have norm 1. So the idea is to like iteratively bound this delta tau so that we have like a guarantee for each tau. So why don't we write out what this delta tau looks like? So we want to construct a recursive formula and express delta tau plus 1 as a function of delta tau. Then delta tau plus 1 equals to G tau plus 1 transpose inner product with Q tau plus 1. Square, right? This is a direct consequence of the formula here, because this is in the orthogonal complement space of U. So what is that? We can use this formula because this Q is just a normalized version of S in the algorithm. So Q tau plus 1 equals to S tau plus 1 divided by the norm of S tau plus 1. Yeah, then we can substitute this into the equation and get like G tau plus 1, S tau plus 1 inner product square divided by S tau plus 1's norm square. And this S plus 1 norm square is, can be further decomposed by projecting this S tau plus 1 onto the true underlying subspace and this orthogonal complement space. And then I can replace it with 1 minus delta tau. Sorry, I'm skipping steps. This is just the inner product of U and S, so it's equivalent to projected to the space. Oh, it's not projection, but instead to compute the magnitude of the component of S tau plus 1 in the space. Yeah. So this is equivalent to the norm of S, since these two are perpendicular to each other. Then the idea in the proof is to, first of all, we notice that this assumes a form like C plus X form. When X equals to this thing, and when there is also an X in the denominator. So all we need to do in order to upper bound this is to provide an upper bound to X and to provide a lower bound on C. So this means that we need to bound the two components of S tau plus 1 onto U and onto its orthogonal complement. So in order to do that, we need a couple of lemmas. So these lemmas give us a concentration of measure, and that's the entire working horse here. And after we bound these, we can express the bond as a function of delta tau, then we have a recursive formula. Then we will simply use the induction to say that this thing is smaller than some ratio to the power of tau delta 0. And so if delta 0 is not crazy, it will converge to 0. So that's a main idea in the proof. But let me just walk you through the details. Lemma A. One minus C over T. Does it fit in here? Yeah, it does. Suppose minus U yeah. Can you all see the equation? And this part is our estimate here. This part is simply the output of the inner loop here. Because we are like adding the xt transpose times qt together, and then it's equivalent to we sum them and then divide it by b. So that block is equivalent to the output of the inner loop. So what this lemma says is that the output of the inner loop in each and every iteration gives us something close to the underlying covariance matrix. And this UU transpose, if we look at the model, it is just the covariance matrix that we want to estimate. So this lemma says that the inner loop works, because that's what we try to estimate to mimic the effect of the power iterations. So lemma B with probability again 1 minus over t, then yeah, it's in fact very easy to see the proof to this lemma. What you need to do is to simply plug in the definition of xt, and then you'll see that the expectation of this thing equals to 0, and then you can bound the variance of each component individually, then plug in the assumption that we made that b needs to be equals to the scale of that, and then you'll get concentration. So it's very easy to prove. So the second lemma is, it says tau plus 1 yeah. The second lemma is slightly more technical. It gives a recursive formula that says that the US tau plus 1 is greater than that. But look at what is this. This is precisely what we want, right? We want to lower bound this term that appears here. If we can lower bound C and if we can upper bound X, then we have replaced all these terms with their lower bound and upper bound, then we have an upper bound of the whole thing. So the second lemma simply gives us a lower bound of this term. That is a projection of S onto the direction U. So that's precisely what we need. And the proof to this lemma B is, again, just plug in the definition of S, and then expand the term, and then compute the expectation, and then try to upper bound those. And one of the term will be an IID chi-square distribution, and the other term will be like the product of two uncorrelated and perhaps independent Gaussian random variable, and with a pretty well-known like random matrix theory result, we are able to upper bound both those two terms, and we sum the upper bound of lower bound of it's actually an upper bound because in the proof they need to shift this over to the other side. But anyway, the proof of this is slightly more technical than the lemma A, but it's not very hard to see either. And the third lemma. Or lemma C. The lemma C gives another statement by saying that with probability greater than 0.99, then we have the inner product of two Gaussian random vector that is normalized to norm 1. Absolute value, this thing. Usually we give an upper bound of this thing to say it is smaller than something. But here what we actually need is that it is greater than some universal constant C0 divided by square root P. By simple concentration of measure, it can be seen that with really huge with overwhelming probability, then we can show that this thing is upper bounded by some other C1 over square root P. But the lower bound is trickier. You only have constant probability. But given the constant probability, then we can show that the random inner product is in the same scale on the lower and upper bound. So this is what they use to prove that if you generate a random variable, a random vector Q0, then the original inner product of Q0 with and U will be lower bounded by something. So if this is 0, then all the power iteration will not work. So this is crucial. With that, and we already have a lower bound of that, and we need another upper bound for this. All these things are just tedious projection of vectors to their underlying subspace and its orthogonal complement, and try to bound the component of the orthogonal complement. And then by induction, one can show that this delta tau goes to 0 as tau goes to infinity, and at a certain rate that depends on at certain rates that depends on something that looks like this. Delta sigma square plus 3/4 and sigma over sigma square plus half. So here's how the argument goes. we want to show that this G tau plus 1 transpose S tau plus 1, we want to upper bound this. And it equals to, if we substitute in the definition of S into it, this is just S. If we times the T at the Q at the back, then this is just S. So I'm simply replacing this S tau plus 1 with this definition. Okay, and this equals to and M is simply the underlying covariance matrix. And this ER is constructed so that the equality is satisfied. So ER equals to M minus E over 1 It's just a meaningless transformation. And now by lemma A that is up there, we have the spectral norm of ER. It is lower bounded by epsilon. Yeah, and this is equivalent to say if we further expand the term into G tau plus 1 transpose M Q R minus G tau plus 1 transpose E R Q tau, then we can bound this term by taking the norm, make it a sum, taking the norm, and this is a unit vector, this is a unit vector, and all this says that this term is smaller or equal to epsilon due to lemma 1. And this term this term, if we replace M with U transpose plus I plus delta square I in here, and we will get like because this G tau plus 1 is orthogonal to U, so the inner product of these two gives you 0. So this term go away, and we are left with just this term, and this identity matrix. So the whole thing is upper bounded by sigma square square root delta tau, and this delta tau is just a definition of G tau inner product with Q tau. Because that's how we define delta tau. It's like the projection of Q tau into G tau, like the amount of energy that is outside the true subspace we are looking for. And because of this, and we have epsilon here. Now good, we have both an upper bound for X and a lower bound for C, and we will have like an overall upper bound for delta tau plus 1. And it turns out that the delta tau plus 1 is smaller or equal to delta tau gamma square over 1 minus delta tau plus delta tau gamma square, where gamma equals to the ratio of sigma square plus 4/3 and sigma square plus half. So all this is saying is that now we have like a recursive formula that transform delta tau to delta tau plus 1 with some large probability. For all the probabilities in this claim, what they did is to simply apply union bound and sum all the failure probability together. So we don't need to worry about it at the moment.